going to be taking a look at graphing the rational function f of x equals x over the quantity x squared minus 1. And the thing that I'm going to start out with here first, you always want to consider vertical and horizontal asymptotes. So we'll look at vertical asymptotes first. Remember, vertical asymptotes take place when the denominator is equal to 0. So I need to figure out what's going to make x squared minus 1 equal to 0. You could use the quadratic formula, but in this case it factors. It's a difference of squares. The quantity x plus 1 times the quantity x minus 1 equals 0. And so x is not allowed to equal either 1 or negative 1. And of course, in this case, those are my two asymptotes. As far as horizontal asymptotes go, remember the horizontal asymptote can be found by taking the limit as x approaches infinity of the function. And if you look in this case, the limit as x approaches infinity is going to increase much faster in the denominator. So as a result, the denominator is going to go to infinity faster, which means that that fractional value, if the denominator approaches infinity faster, it's going to approach 0. And that's a horizontal asymptote, so that's y equals 0. So when I put together my graph for this, I know that there are going to be asymptotes at negative 1 and positive 1 on the x-axis, and I'll set my scale negative 1 here and positive 1 here to make this wide enough to fit a little bit of graph in. And so there's a vertical asymptote. I'm going to plot that, and here is another vertical asymptote, and then my horizontal asymptote is going across here. Wouldn't be a horrible idea to do that in another color, but anyway, we can see, so there are my asymptotes. So, I'm going to have graphs maybe going like here or here, maybe something like this, or cutting through like this, here maybe, or here maybe, something like that. Honestly, from an Algebra 2 standpoint, you can really just start plotting some points here if you put them in the equation, and you can get a pretty good idea of what the graph is going to look like. We're going to do a little bit more analysis here because we are in a calculus class, and we can do that. So the first thing I'm going to do is try to find if there are any relative maximum or minimum values. So specifically trying to find out, is the graph going to change direction at any point? And of course, you can find out when the graph changes direction. The direction is told you by the derivative. So I can find f prime of x. Now the original function, if you remember, is a rational function. Using Forester's approach, you take the derivative of the top, which is 1, times the bottom, which is x squared minus 1, minus the derivative of the bottom, which is 2x, times the top, all over the denominator squared. And I'm not going to multiply out the denominator. I'm going to keep it in that form. I think this is actually going to make this a little bit easier. In this case, that's going to be a negative 2x squared. So 1x squared minus 2x squared is going to be negative x squared. I have a negative 1 here, nothing else being subtracted. So negative x squared minus 1 is my numerator. And then my denominator is going to stay x squared minus 1 squared. And you're really going to have to use some common sense to decide whether or not you need to multiply that out or leave it in factored form. And it really just depends on what you're trying to accomplish. But in this case, I'm going to leave this in that form. Now I'm going to make my little table here, f prime of x, and I'll find out where my graph is rising and where my graph is falling. Remember, anywhere where the derivative is 0 or undefined, I'm going to have a solution. Well, first of all, if you go back and you set this equal to 0, you've got negative. I'm going to factor the negative out of the x squared minus 1. I'm going to write that as x squared plus 1 over x squared minus 1 quantity squared. Remember that anywhere that the derivative is equal to 0 or undefined, you're going to have critical values of x. And in this case, the only thing that's going to make this fraction equal to 0 is if the numerator is 0. However, notice any negative there is going to give me a positive. Plus 1 will give me something greater than 0. If that's 0, it's going to give me 1. Anything bigger than 0 is also going to give me 1. Point being, I can't get a negative here. Actually, you get negative or positive I there are the only numbers that would work. And of course, those are imaginary. So I'm not going to get derivatives of 0. However, I do have an undefined derivative because this denominator factors as the quantity x plus 1 times quantity x minus 1, both of those being squared. And so x cannot equal negative 1 or positive 1. So once again, I need to consider those values. So when I make my table here, I'm going to look at negative 1 and I'm going to look at positive 1. And if I substitute into my equation, for example, I could pick a number like negative 2 and substitute it back into f prime. And if I substitute a negative 2 into f prime, you can see that I'm going to get a negative value. So the graph is going to be going downhill. If I substitute in something between negative 1 and 1, maybe something like 0, you can see that I'll get a 0 numerator there. Well, I'll get a 0 when I substitute in for x, and then when I subtract 1, I get a negative. Denominator, because it's being squared, is going to end up being positive. So a negative divided by a positive still gives me a negative. So interesting, this thing is still continuing downhill. And when I put in a value greater than 1, I could substitute something in like 2. F of 2 here, actually, interestingly enough, also ends up being a negative value. And so I end up with my graph going downhill in all directions, which is interesting. So it tells me something. Now I can also take the second derivative, and I'm going to be taking my derivative of this function. I'm actually going to use this version of the function, not in factored form. I think that'll make it a little bit easier. So f prime of x is equal to negative x squared minus 1 over quantity x squared minus 1 squared. And now I'm going to take the second derivative of this. This will be fun. Going to need to use the quotient rule again. Derivative of the top is negative 2x times the bottom, which is x squared minus 1 quantity squared, minus the derivative of the bottom, and that's going to be 2 times the quantity x squared minus 1, lower the power by 1, times the derivative of the inside function, which is 2x. So that's the derivative of the bottom times the top, which is negative x squared minus 1. So the derivative of the bottom times the top, and all of that is being subtracted. We can simplify this just a little bit here. Let's see, that's going to be 4 times 4x times x squared minus 1 times that negative x squared minus 1. And I have the negative 2x times the x squared minus 1 squared minus all of that. And then that's all over the denominator squared, which in this case, the quantity x squared minus 1 squared, if I square it, will be to the 4th power. And again, I want to try to simplify this thing a little bit. I'm actually going to do a little factoring. I noticed here that I can divide out a negative 2x from both of these. I can divide out an x squared minus 1, and that'll simplify things down a bit. So I'm going to divide out the negative 2x and the x squared minus 1, and that's going to leave me with just the x squared minus 1 minus, if I divide a negative 2x out of here, that'll give me a plus 2. The x squared minus 1 is getting factored out, so that's gone. And I have the negative x squared minus 1. And that's what I have. And let's see if I can simplify a little bit here. 2 times negative x squared is negative 2x squared. 2 times negative 1 is negative 2. So that's going to be x squared minus 2x squared is negative x squared. I have a negative 1 minus a 2 is minus 3. And I have my negative 2x times x squared minus 1 on the outside of parentheses here. You could possibly divide this negative out of parentheses here. Of course, you would have a negative 2x then. That would give a positive 2x times the quantity x squared minus 1 times the quantity x squared plus 3. And remember what I'm trying to do here. Of course, all of that is over the denominator squared from before, which is that x squared minus 1 to the 4th. If I wanted to, I could cancel an x squared minus 1 there. Would simplify things a little bit. Actually, I do want to stop here, though, and take a look at a few things. First of all, now I'll go ahead and simplify that down. That's 2x times x squared plus 3 over x squared minus 1 to the 3rd power. Okay? Now, remember this is the second derivative. The second derivative gives me the concavity. When the second derivative is equal to 0 or undefined, I can use those points to find my concavity. So if x is equal to 0, the numerator will be equal to 0. Notice x squared plus 3, a negative value won't work here to give me 0. 0 won't work, and a positive value won't work. So that's an imaginary solution that would make that equal to 0 if I was trying to get a 0 here. And so I don't really need to worry about that. Meanwhile, anything that gives me a solution of 0 for the second derivative or undefined, notice that denominator factors into the quantity x plus 1 times the quantity x minus 1, each of those cubed. So x is not allowed to equal 1 or negative 1. So once again, I have to check between negative 1, 0, and 1 for my graph, for my concavity. So I'll put together my number line here. And I have my f double prime of x. And I have my negative 1. I have my 0. And I have my positive 1. And if I check values, if I check something like negative 2, I get a negative value, which is concave down. If I check something between negative 1 and 0, like negative 1/2, I actually get a positive value, so that's concave up. If I check something like 1/2, I get another negative value, so that's going to be concave down. And then if I check something greater than 1, I end up getting a positive value, which is concave up. And again, if you substitute into the factored form, it will actually save you some time because you just have to determine the sign. So for example, if I put negative 1/2 in here, I'm going to get a negative when I substitute in for the 2x. I'm going to get a positive, so it's a negative times a positive on top. On the bottom, if I put negative 1/2 in, I'm going to get a negative cubed, which is a negative, and that ends up giving me a negative divided by a negative, which is a positive. And you can see that's how I got my value between negative 1 and 0. So I did that work ahead of time to save a bit of time, but that's the basic idea. Okay, now I have these two charts, and basically you can plot some points here. This is a place where if you do have a scientific calculator, you might want to use it. Of course, if you've got a graphing calculator, you can even cheat, but you can plot some points here and get a better idea of what's going to happen. I'm going to try to plot a point or two below negative 1, a point or two between negative 1 and positive 1, and I'll also do a point or two after positive 1. If you have a graphing calculator, and again, a lot of times you might be doing this by hand, and hopefully it's a pretty easy equation. You can, of course, put your equation in your calculator. This is x over x squared minus 1. And you can use your table. I'm going to go to table set. I'm going to put this on ask. And when I go to my table, it's going to allow me to insert values. So for example, if I want a value before -1, I could put in something like -2. And that's going to tell me -2/3. So -2, -2/3. And I can plot that on my graph. Maybe I'll make this -1. I'll make this -2. So let's see, we're at -2, -2/3, maybe something kind of like this. And then, you know, I might try a point a little bit closer. I know if I go back and look at my original analysis, the graph is supposed to be sloping downward, and you can see here it's concave down, so it's probably going to be doing something kind of like this, approaching that asymptote. Pull back here. Approaching that asymptote. And again, you might want to plot another point or two, but something like that usually will suffice. Okay, and meanwhile, I want to try a value or two between -1 and 1. If you go back and really, and a lot of times you'll get something symmetrical that looks like a parabola or something like that. So I'm going to try some values on either side. I'll try -1/2 on my calculator, and I'll try 0, and I'll try +1/2. And interestingly, you'll see here that -1/2 and +1/2 give me, -1/2 gives me 2/3. So that'll be up here. So -1/2, 2/3. Interestingly, +1/2 gives me -2/3. Oh, let's see, I spaced this out a little bit differently here. Let's make that 1, and we'll make 2/3 about right here. Let's see, +1/2 gives me -1/3. You can try a few more values. You might try something closer to -1, like -0.9, and you can see that you get a larger value there. If I try something like +0.9 on my calculator, you can see that I get a very negative value. So basically what this graph is doing, and if you look at your concavity, you should be able to tell this graph is going downhill for the entire section between -1 and 1. And you can see, though, that the concavity is going to change at 0. Okay, and in fact the point 0, 0 is on this graph. And so what's going to happen here is it's going to be downhill. It's got an asymptote going in this direction, downhill. If you notice the original, it's concave up. I have it concave up here. And then it changes to concave down, and it passes through that point there, and it approaches the asymptote. Probably going to look something kind of like that. And then I need to try something above 1. So maybe I'll put something like 2 into my calculator, and I find out that that's 2/3. So if I go over to 2, and then about 2/3 the way up, so I guess 2 would be about right here, 2/3 would be like this. And if we look at it, it's going to be a downward sloping graph, and you can see that it's concave up. So that should be doing something kind of like this, again approaching that asymptote. And you can always plot a few more points. Let's see when we graph this thing if that looks anything like what it's supposed to look like. Yeah, you can see the scale there is a little bit different, a little bit tighter scale there. I had my window spaced out a little bit more, so I could change my X values there to have a slightly thinner window. And then you can see that the distortion is a little bit more like what I drew. But anyway, graph looks something kind of like that. So the key, draw your asymptotes, vertical and horizontal. Take your first derivative, find your turning points on your graph if you have any, then find your second derivatives and get your concavity. And you can test a few points, plot some things, and get a graph. Not very fast, but not necessarily all that difficult either.